Hello and welcome again to the lecture course on Relativity and Cosmology. Last time I introduced you into the Penrose process by which you could extract energy from a rotating black hole, making use of a special region outside the event horizon, and this special region is called ergosphere. We have also seen at the end of that subsection that during the Penrose process the area A of the rotating black hole is changed and by dA, and we have given that formula first derived by Christodoulou, 8 pi over kappa, where kappa is the surface gravity which I had defined, and then you have dm minus omega h dj, the angular momentum of the horizon, and then the respective changes of mass and angular momentum. And the important property of this, that this is non-decreasing in that during the Penrose process. Now the question is, and it will actually be answered in the affirmative, whether this holds much more general than just for the Penrose process, and this is encoded in a theorem that I only quote. I mean, we have no time to prove this mathematical theorem by Hawking in 1971, that assuming a certain energy condition, which I wrote down, the area of a future event horizon is non-decreasing, quite generally, independent of this particular solution. So, assuming the weak energy condition, which in this case is for light-like vectors, so which means that r mu nu k mu is non-negative for all light k mu, obeying k mu equals 0, the area of a future event horizon in an asymptotically flat space-time is non-decreasing. So, I mean, here we have the special situation of the Penrose process. Here we have Hawking's general theorem. Now, I want to remark that here the presence of an event horizon is assumed, so cosmic censorship is implemented. Recall, cosmic censorship means that you cannot see singularities from outside, so there should be some horizon where they are hidden. So this is implemented, and also there's a time direction implemented, because here this theorem refers to the future event horizon. Recall, for example, in the Schwarzschild case where we have the future and the event horizon. So then the past event horizon, so the black hole case and the white hole case. So we don't talk about white holes here, we talk about black holes. Otherwise, of course, a similar theorem would hold, but just with the opposite here for the white holes. This has consequence, this theorem, so you can, for example, if you have two black holes coalescing with, well, this is only symbolized here with areas E1 and E2 respectively, and if they so merge and so to one black hole A3, so well, independent of the details of this process, we conclude from Hawking's theorem, which is also applicable to this situation, that A3 is bigger or equal than A1 plus A2. And as you will see in our last section in the black hole chapter on astrophysical black holes, this has been observed by the emission of gravitational waves. And as far as one can observe, this so-called area theorem by Hawking is always fulfilled. Okay, that's interesting, but why do I here write thermodynamics? Well, I mean, you know from standard physics, I mean from your early classes on, that there's a very central quantity called the entropy, of a thermodynamical system for which a similar law holds. So if we have here the analogy with thermodynamics, and there of course for closed system we have the second law of thermodynamics. Now, but you may say, well, this certainly has nothing to do with here. I mean, this is a theorem here about differential geometry, and here, as you know, the foundation of this comes from microphysics, from the counting of states by Boltzmann's law. But nevertheless, it was very early speculated, and very early, more or less, only Bekenstein took this analogy seriously in a couple of very important papers, the beginning of the 70s. So how come? I mean, Bekenstein was a student of John Wheeler. Like many good and brilliant young physicists, they were with John Wheeler, who provided them with intriguing questions. And so John Wheeler asked, okay, what happens when I throw a cup of tea into a black hole? Now, a cup of tea, I mean, has certainly an entropy. We calculate this in elementary classes. And but if we throw this into a black hole, then of course it has disappeared. The entropy of the black hole, well, it does not seem to have any meaning. So you can reduce the entropy in the universe by just throwing things into the black hole. And that this would be a violation of the second law. And Wheeler asked, can this be? And Bekenstein thought about it and said, no, we must attribute an entropy to the black hole. And he devised very intricate and clever Gedanken experiments for that. But very people took it at that time seriously. But there was the next step was that people found out that there's not only a formal analogy between that law here and this law here, but also actually between all laws of thermodynamics and corresponding laws of black holes. So there are analogies to all laws of thermodynamics. Now, this was discussed and proven in an important paper by Bardeen, Carter, and Hawking in 1973. And yeah, there is the first, the second law, but it's also the third law, and we even have a so-called zeros law about the temperature. So, I mean, the zeros law says in thermodynamics there's a quantity that is constant all over the body in thermal equilibrium, and this is the temperature. And actually there's an analogy, and this is this kappa, the surface gravity, that we have here defined for the Kerr black hole, but that we can define more generally. So kappa, the surface gravity, is constant on the event horizon. So we can, in a sense, have the analogy between kappa and the ordinary temperature of a body. Now the first law is about energy conservation, and yeah, well, if I rewrite this somewhat in terms of the change in m, so we have kappa over 8 pi. So I just use here the ordinary d as is typically used in the books, dA plus omega dj. And if you have a charged black hole, I mean, you have even a term minus phi, the electrostatic potential, and dq. So this is the electric charge. As for the full Kerr-Newman black hole, and this of course corresponds to the energy law, dE, which is T ds minus P dV plus mu dN in the standard meaning of the symbols. So we have here this first law. So look at this term here. So we have already tentatively identified kappa with T, I mean up to some factor. So if we have here kappa corresponds to T, then of course we should associate A with S, no? Just from these two terms. And of course this association of A with S corresponds here to that analogy with the second law. And let me just for completeness write the second law here again here, which means dA is non-negative. You know, so you see, at least for the formalism suggests that we have a quantity kappa that is like temperature and a quantity A that behaves in certain aspects like the entropy. Okay, there's also a third law which says something about the in thermodynamics, about the unapproachability of the absolute zero of temperature by thermodynamic processes. And one can also prove here that kappa equals 0, which would then correspond here to T equals 0, cannot be reached in a finite number of steps. That actually corresponds to the formulation, the original formulation of the third law of thermodynamics by Nernst, Walter Nernst of 1905, that T cannot be reached, and the same sentence. Now there's another form of the second law by Planck, as actually a stronger version. So stronger version by Planck, 1911, which says that S, the entropy goes to 0 if you approach the absolute zero of temperature. But this law that S going to 0, I mean, this is violated here. Actually, it's violated also in many cases of ordinary thermodynamics, because you find systems where that have a non-vanishing entropy at 0 temperature, like glasses. So if you still have some degree of disorder, and so even at absolute 0 temperature, but this is also violated in here. Now here, for example, if you go to the extremal black hole, say Kerr black hole is kappa to 0, which corresponds to temperature to 0, but the extremal black hole still has an area. There's no non-vanishing area, so S goes to A actually over for kappa to 0. Okay, that's I mean, I'm too early here, because that's actually the next step. But I can already mention it here that here this is violated. So. Well, independent of this exact expression, the area of the extremal black hole is non-vanishing. Now, in 1973, people found that very interesting, but considered it as a pure formal property. So black holes seem to behave like thermodynamical systems. I should for clarity say this is about stationary black holes. I mean, stationary black holes that are characterized by few parameters, so they have lost their hair. And in fact, there is a theorem that we should mention, a theorem that was proven somewhat earlier than that. I mean, that was an exciting time for understanding black holes, so between 1965 and 1975 for classical black holes, where many of those theorems were proven. And let me only mention it here. So there is a famous uniqueness theorem that also called, I think again, invented by John Wheeler, the no-hair theorem. It will become clear why no hair. And it says that stationary black holes are uniquely characterized. I mean, stationary black holes in Einstein-Maxwell theory. That means Einstein equations coupled to the energy momentum tensor of the electromagnetic field by just 3 parameters. So independent of the origin of the black hole, if you have a star with many degrees of freedom, this is called a hair, then by the collapse all this hair is radiated away, for example, in the form of gravitational waves, and only these three parameters remain. So it's actually a three-hair theorem, not a no-hair theorem, but people call it no-hair theorem. So stationary black holes are uniquely characterized in Einstein-Maxwell theory because there are, if you couple other fields other than electrodynamics, for example, non-abelian fields, I mean, that you have in quantum chromodynamics, it no longer holds in Einstein-Maxwell theory by the three parameters: mass, angular momentum, and electric charge. Okay, if you had the magnetic monopoles, which we will not assume, then there would be also the monopole charge here, but I leave that out. There are many people involved, end of 1960s, beginning of 1970s, who proved various aspects of this. And if you want to read the technical details, I can recommend a very good book by Markus Häusler on black hole uniqueness theorems, which appeared with Cambridge University Press, I think, in 1996. I have not written it here, but I think it's around that time. Now, the most exciting thing happened in 1974, because in that year Stephen Hawking could show that there's actually more than behind than just an analogy. Actually, black holes are thermodynamic system, and he showed this by bringing quantum theory into the game, so using quantum field theory in curved space-time. So this is something that goes beyond our lecture course. This is why it's only mentioned here, but it's so important that I will give you some key formula. So interpretation by bringing quantum theory into play. So this Hawking's famous result of 1974, that black holes in fact radiate, and that they have a temperature, and therefore also by the first law in entropy. So he showed that black holes have a temperature which we call the Hawking temperature, and it's given, you see, h bar explicitly occurs, h bar kappa over 2 pi Boltzmann constant, the speed of light, so putting all the constants. So that's the Hawking temperature. And yeah, by the first law, I mean, if you replace here kappa by this expression, then it's clear, I mean, what is the relation between A and the entropy? And the entropy, which we call SBH. So BH can stand for black hole, but also for Bekenstein-Hawking, because Bekenstein was the one who came up with the idea, and emphasized that it should be proportional to the area, but the exact free factor could only be calculated after Hawking had this found this temperature. So this is A c cube over 4 g h bar, or if you introduce so-called Planck lengths, you can write it as A over 2 twice the Planck length squared. No, so the Planck length squared is gh bar over c cube, defines a fundamental length. And okay, so let me call this the Bekenstein-Hawking entropy. For Schwarzschild black hole, I mean, the kappa, I wrote this down to you earlier, it's 1 over 4 gm. And we get the following results. So for the Schwarzschild black hole, we have TH, which is then turns out to be h bar c cubed over 8 pi kb gm, which numerically, if you insert numbers, 6.17 times 10 to the minus 8, if you measure the mass in terms of the solar mass, Kelvin, and the corresponding entropy is kb times pi Schwarzschild radius squared over g h bar, and numerically it's about 1.07 times 10 to the 77, the mass in terms of solar mass squared kb. No? So here, what do you see from this? You see that the mass occurs in the denominator. That's very strange, it seems, because it means that, I mean, the black hole radiates thermal radiation, and of course the energy of this comes from the mass of the black hole, so the mass must decrease. But if the mass decreases, the temperature becomes bigger because the mass is in the denominator, so the object becomes actually hotter by radiation. I mean, that's not what you know from your cup of tea, right? If you leave your cup of tea for a while, it does not become hotter, it becomes cooler. But this property, I mean, that objects can become hotter by radiation, is not uncommon for gravitational systems. So, and it has to do with the negative gravitational energy in a loose sense. For example, if you have a satellite that goes around the Earth, and there is some friction in the atmosphere, and by this, I mean, the gravity, the satellite goes to the lower orbit, but it becomes faster. So it becomes, by this friction, faster than, not slower. Now, so this has to do, of course, with gravity. Now you see here the entropy is proportional to m squared, and is very big. So for a solar mass black hole, this would be around 10 to the 77 in units of Boltzmann constant. Now the entropy of the sun is basically given by the number of particles in the sun, which is around 10 to the 57. So this means that an object with solar mass, if it could collapse to a black hole, it would increase its entropy by 20 orders of magnitude. So that's a huge increase of entropy and of disorder. So you cannot reach that in your room by creating all the disorder that you can do in your room. You will not be able to increase it in such a way. Now, we need a theory we need quantum theory, and eventually we need quantum gravity to get final insight into that. And that's not a topic of the lecture course on general relativity, but I plan next summer in 2022, to offer a specialized lecture course on quantum gravity. And of course, there we will address, among many other things, this year. Okay, so far for 11.6. Now the next section, 11.7, is devoted to the gravitational collapse to black holes, and how we can adapt coordinates, especially to the collapse situation in contrast to the stationary situation. So the next section is going beyond stationary black holes, discussing the gravitational collapse to black holes. As we have seen in the first section in chapter 11, so if a star collapses, because all the nuclear processes end, it can stabilize to a white dwarf, or it can also stabilize to neutron stars if the mass is not too high. So roughly the limit is about 3 solar masses. But if the initial mass is bigger, according at least to general relativity, and if there's no new speculative physics coming in, the collapse leads to a black hole. So collapsing object, I mean, for mass, okay, this would have to be discussed in more detail where exactly the limit is, but let us assume it's, I mean, after all, of course, the other mass has been emitted. The collapsing object has 3 solar masses, then it will end up to a black hole. Leads to a black hole. We would, of course, like to describe this process within general relativity. let us assume, for simplicity here, spherical symmetry, no charge, so we have a Schwarzschild black hole. Here, for simplicity, Schwarzschild black hole. Now the question is, of course, do we need to take into account non-gravitational processes to understand that? And in general, we expect this. For this purpose, let us consider the density of an object when it reaches the Schwarzschild radius. Density at the radius, I mean, of that spherical symmetric star, for the Schwarzschild radius, which is 2 gm over c squared. Of course, the radius can be written as 3m over 4 pi rho the 1/3, just by using the definition of the density and rewriting the volume of a sphere. Then, and we demand that to be equal to 2 gm over c squared. So, of course, this in coordinates is just a heuristic estimate, and we take this to be constant, say, for this estimate. Then we find here that rho is 3 c to the 6, 32 pi g cube m squared, which, if you insert numbers, is roughly 2 times 10 to the 16 gram per cubic centimeter, solar mass over mass squared. Now, so you see here the mass enters quadratically in the denominator. If this is of order solar mass, then this density is quite high. Now, if you have then the object has such a high density when it reaches Schwarzschild radius, means that non-gravitational interactions are not negligible. So we would have to take them into account. But if we, for example, consider a whole galaxy, say with 10 to the 11 solar masses, then this is very small. So this here is, if you have here m, so this is very high, so need to take non-gravitational processes into account. But if you, for example, have here m of the order of 10 to the 11 solar masses, which is a galaxy, a typical galaxy, then rho is of the order of 10 to the minus 6 gram per cubic centimeter, so that's already a very small density. So what I want to say with that is that if the mass is sufficiently high, then even if the object collapses, I mean, to the Schwarzschild radius, the density is so low that we can restrict to the gravitational description. Of course, this does not mean that we cannot do also the general process, but for simplicity, just have in mind that we have here such a situation, so we can neglect non-gravitational processes and consider the collapse as a pure free fall. So consider collapse as free fall. This of course enables then to devise a simple model. In fact, the first model, a very famous one, was proposed by Oppenheimer and Snyder already in 1939. So they, for the first time, considered really the collapse to a black hole in general relativity. So the first model by Oppenheimer and Snyder in 1939. So they considered a pressureless star of spherical symmetry collapsing to a black hole, and so they had outside the Schwarzschild, I mean this collapsing object, before it becomes a black hole, outside of course Schwarzschild by the uniqueness of Schwarzschild, and inside they could have then the Friedmann solution, or what we then will learn in cosmology, I mean the line element of cosmology, which in fact you have already seen in the form of the Tollmann-Oppenheimer-Volkoff solution. So that they consider the collapse of a pressureless star with spherical symmetry to a of pressureless star and uniform density. Yeah. I will not describe this solution in detail, but you can think about this solution as presenting a concrete realization of what we discuss. So if you have a collapsing situation, then for the if you have in mind a full Kruskal diagram, as I mentioned already earlier, only part of that diagram is needed. In fact, only the regions 1 and 2, and not the regions 3 and 4. So here, if you recall, we have here the Schwarzschild radius, and we had also the singularity, which for the Schwarzschild was a space-like, and it was like that. Oh, so that's the singularity r equal to 0. So if you start with a star at initial radius here, so an initial proper time, and r equals r, so the initial radius of the star would be then here like at that coordinate, so that would be r equals r, so this is the stellar radius at the t equals 0. And of course the star will collapse, so the stellar radius will decrease, and so it will move, say if it's free fall on a geodesic, and end up to the singularity. No? So that's the stellar radius. That's the picture. Now, as I said, this is free fall, so they move on geodesic. So you can calculate, the curve here. In the Schwarzschild metric, we have discussed geodesic in the Schwarzschild metric, so this is in principle doable. Doing that, one can calculate the proper time it takes from here to reach the singularity. And if you calculate the proper time, you find it has a finite value. So the surface of the star falls through the Schwarzschild radius and reaches r equals 0 in a finite time. I just give you the result. You find it from our earlier equations. So this means that after a finite proper time, the surface falls through the Schwarzschild radius and reaches r equals 0 after a time, well, I should call this perhaps tau, the proper time. Tau is pi square root of a r cube over 8 gm. So rather simple formula. Of course, this does not hold for an external observer, as I have discussed when discussing the Kruskal diagram. That the external observer maybe stays here at r equals capital R, and the external observer, of course, when you cross here, you will no longer be able to see signals that are sent here in the inside. I mean, this signal will stay here on the light cone, so you will see the star approaching the Schwarzschild radius. I mean, slower and slower without reaching it. Well, if you have a star of constant density, so rho is constant, then you get here that tau is pi over 2 square root of 3 over 8 pi g times rho. Just replace r cubed by 3m over 4 pi rho. We had this earlier here, this relation. And numerically, this is around 2 times 10 to the 3 if you measure rho in terms of gram over cubic centimeter to the minus 1/2 seconds. So that's but then a rather short time. I mean, if initially, say, rho is of the order of 1 gram per cubic centimeter, then this tau would be of the order of 1 hour. So that could be the value, say, for the sun. And it's called in astronomy the free fall time. I mean, that you can already estimate from Newtonian considerations. I mean, before you discuss Schwarzschild radius and the like. Okay, so that's the free fall time. Now, recall the Kruskal coordinates. They would cover much bigger region than just this. No, I mean, this we call the region 1 and this the region 3. So they're not really needed in their full generality. And this is why people prefer also alternative coordinate systems. And as you know, in general relativity, we can use many coordinate systems to study collapse. And one appropriate coordinate system is called Eddington-Finkelstein coordinates. Yeah? So appropriate for studying collapse, so-called Eddington-Finkelstein coordinates. There's an ingoing version and an outgoing version. For the collapse, we use the ingoing version. So, the outgoing version would correspond to the time reversed version. Okay, so how are they defined? Well, again, as with Kruskal, we need two steps. So in the first step, we actually it's the same step as we had when we're going to Kruskal. We introduce this tortoise coordinate r star that you already have encountered as r plus 2 gm, and then we have this logarithm. So this means that the outgoing radial null geodesics, they propagate on t minus r star equals constant. I mean, these coordinates have the property that the light rays, they are on the straight lines as in the coordinates as in flat space-time. Now in flat space-time, so flat space-time, we can use this light coordinates u is t minus r and v is t plus r. And here the same holds, this straight lines, if we replace r by r star. But then of course we give this a new name, so it's u tilde and v tilde. So outgoing radial null geodesics propagate on u tilde, which is defined as t minus r tilde. R star is constant. And the ingoing radial null geodesic, they propagate on v tilde, is defined as t plus r star. So that's the first step, already known. And the second step is now the new one that leads to Eddington-Finkelstein coordinates. We take r and v tilde, well, instead of r and t. So use r and v tilde instead of r and t. Now, so this v tilde here is the new second coordinate here. No, this v tilde. So and if you use that, I think it's a simple calculation. Just go back and look how the Schwarzschild looks in terms of r star, and then you use this linear relation to rewrite it in terms of v tilde, and go back using r, and so then we have ds squared is minus 1 minus 2 gm over r v tilde squared plus, now we have importantly a non-diagonal term 2 dv tilde dr, and plus r squared the omega squared. Now, so that I have to emphasize that we have now non-diagonal term. I mean, this is the standard term, and we have this is also standard term. But of course, this is a light-like coordinate, and this is why we have this mixture. And if you take r to infinity, so you are far away from the black hole, then you find Minkowski space back, but Minkowski space in terms of the null coordinate v tilde, which means that and v tilde then becomes the v. So far away from the object, you have minus dv squared plus 2 dv dr plus r squared d omega squared. Let us consider the radial light rays then, their trajectories. So radial light rays, they obey ds squared equal to 0, of course, and if they're radial, they are on constant coordinate values for theta and phi. And if you insert it here, so that's 0 and this is 0, so you can bring this to the other side. So you have 1 minus 2 gm over r dv tilde squared is the same as 2 dv tilde dr. Now that's the relation between v. From this you get the relation between v tilde and r. Now let us have a look. Okay, you see here dv tilde equals 0 is a solution, so we can treat it separately and then divide by dv tilde for the ones with non-vanishing dv tilde. So for the solutions, then you have the first one, a dv tilde over dr is 0, and okay, from this then, and inserting r star, we have that, well, we directly see, and here it's simple. If this is 0, you directly get that v tilde is equal to constant. So t plus r star is equal to constant. So these are the radially ingoing light rays. Radially ingoing light rays, which have here, I mean, constant v tilde, and this is why this version is called the ingoing Eddington-Finkelstein coordinates, because this ingoing, I mean, this variable describing the ingoing rays is constant, but the outgoing, you would have the same for u tilde. Now let me take b, then dv tilde unequal to 0. So we can divide by this here, and this gives dv tilde over dr is 2 over 1 minus 2 gm over r, from which you get that v tilde, if you can easily integrate, this is twice r plus 2 gm logarithm of r over 2 gm minus 1 plus constant. And comparing this with that expression, you see this is 2 r star plus constant. So v tilde, I mean, was defined here to be t plus r star, and we have seen that this is also the same as 2r star plus constant. So we see that we have here r star is t plus constant. So that's the equation for the outgoing light rays. I should note here, I mean, from this you see that also r equals 2 gm is also a solution of this for dr equals 0. And if you have dr equals 0, so constant r, then this is 0, and then of course if this is 0, so r is also a solution. Yeah, the qualitative behavior of this in a coordinate diagram, and we use here the following. So we here plot r, and here we have a coordinate t tilde that is defined as v tilde minus r. So how do the light rays look like here? Well, I mean, from this equation here, you see, I mean, here from this, you get that dv tilde over dr. If you approach infinity, goes to the constant value 2. Yeah. And this gives, I mean, for that dt tilde over dr is a dv tilde over dr minus 1. This goes to 1. I mean, so with respect to this, we have the usual inclination 1. So the dv tilde over dr, if you approach the Schwarzschild radius, goes, of course, to its diverges, so it goes to plus or minus infinity, which means that also d tilde over dr goes to plus or minus infinity. And if you approach the singularity, so r to 0, then it goes to 0, but from the minus side, right? Because you get, I mean, this diverges and it's here negative. This I indicate by this. So this means that d tilde over dr goes to minus 1. And if we depict that in the diagram, of course, we have here the Schwarzschild radius, and this is a solution. So here r to gem is a solution, and we have the outgoing light rays, so they asymptotically go to inclination 1, and otherwise they have, I mean, fulfilled this here, and so this leads to something like that. And here they go to the inside, and they hit this with the inclination minus 1. Now that's here r equals 0. Now the ingoing ones, they are just the radial ones. That here v tilde is equal constant, so t is constant minus r. So the ingoing one, they have then this. And so you can also depict the light cones here, of course, for what light cone would be like that. Of course, far away it's just a standard light cone, but if you approach here, then the light cones become inclined towards the interior. So you see here, I mean, here that's also a light cone, that if you have crossed that surface, then the light cone is inclined towards the interior. And here you get that. So that's then the picture you have in these Eddington-Finkelstein coordinates. Now I mentioned that that we can pass through this in a finite proper time, and that for the external observer this happens in infinite observer time. But so you might say, well, I can see then the collapsing star forever. Well, this is very theoretical because the luminosity of the star decreases exponentially. So it would be within a very short time be extinguished. So we have an increasing redshift that one can calculate. But so z is defined as delta lambda, so that turns out to be e to the 4 gm, well, which is actually 1 over 4 gm is the kappa, so e to the kappa t. So this is for radial light rays. If you take into account also non-radial ones, then we can calculate a full decrease in luminosity, and this was calculated by Ames and Thorne in 1968. So, and then they found L is proportional to the initial luminosity, and then we have this exponential decrease e to the minus, then we have 3 square root of 3 gm. No. So you see the star very quickly becomes unobservable. So there's a characteristic time called t decrease, which is 3 square root of 3 gm, of the order of 2.5 times 10 to the minus 5 m over m sin seconds. You see for solar mass black holes this is really a fraction of a second. So the star becomes rapidly invisible. This is why originally these objects were called dark stars before the name black hole was invented. Dark stars, beginning of the 60s, especially from Russian scientists, and only later when John Wheeler basically promoted calling it black hole, people got acquainted to black holes. But dark star means, a collapsing object that you can no longer see. Yeah, here you see ingoing and outgoing light rays. So understand, without the black hole, if you had ingoing, they look always like that. But if there were no black hole, then if you had here an outgoing light ray, it certainly goes there. But also in the inside, outgoing would go there. The black hole acts differently. If you have an event horizon, even if you are here and you initially, it's maybe not clearly seen here on that initial diagram, but even if you start sending it outgoing, it will return and go inside. No? So that's the typical thing of a black hole. It's also called a trapped region. Trapped region means, and you can generalize this notion, that the light rays are trapped. You cannot send, even if you attempt sending outside, they will end up at a singularity. And so that's of course a particular example, a Schwarzschild and the collapse to a spherical symmetric black hole. So the question is about the general collapse. And of course, as soon as you enter general consideration, it becomes complicated, like for the uniqueness theorems and so on. There are also theorems here, they call the singularity theorems, which is a topic on its own, a very mathematical topic. And let me only write down, some major results at the end, before we then go over actually to observable black holes. So let me end this section with some very brief remarks on general gravitational collapse. You may wish, to have a look, for example, into this book, which is a summarizing book, which grew out of lectures that Penrose and Hawking gave in Cambridge in the 1990s. So it's called The Nature of Space and Time, published in 1996. There's also a German translation, if you like. And so the central question is, what about the singularity that arises here from the collapse? People assumed in early years that things like the Schwarzschild solutions are artifacts of a symmetry assumption, that only because you have a high symmetry you have singularity, because spherical symmetry demands that everything must hit in the center at the same time. And so if that's avoided, then maybe the singularity is avoided. And it was the big merit of Penrose and Hawking and others from 1965 and to show no, the singularities are actually a generic feature. And so Penrose started with this, with 1965, with his famous theorem that is relevant for the black holes, which gave him the Nobel Prize in 2020. Yeah, so after more than 50 years. There are various theorems with various assumptions, and they go under name of singularity theorems. If you like, you can read in this accessible book about that. So this is Penrose 1965, and then Hawking and others. So that's here what brought him the Nobel Prize of 2020 for very mathematical work. And so you need assumptions. So the various theorems, you can distinguish them in what kind of assumptions they use. And you can always discuss whether assumptions make sense or make not. But typical assumptions are the following. Typical assumptions. And there's an energy condition, which in fact, I mean, it's a condition on the energy momentum tensor of matter, typically the so-called strong energy condition. This is the one that is often used for the singularity theorem, strong energy condition. Well, it's just that in the proof for the proof to go through, a certain condition has to be fulfilled, and you see that this is a condition on T mu u, and then you give it a name, and so that means that here that T mu nu psi mu is bigger than -1/2 G mu nu T mu nu for all time like psi mu. So if you have an ideal fluid, this means that, I mean, an ideal isotropic fluid, that rho plus 3p is non-negative, and this is density and pressure. So that's what you typically use. Then there's also B, a condition on the global structure. So, for example, the non-existence of closed time-like lines, so that you cannot travel via your future into your own past. So you can avoid the singularities if you have, for example, that. And the existence of a so-called trapped surface. As we had in the Eddington-Finkelstein diagram, a region where also light rays that you send in the direction of going outwards turn to inwards, so they cannot leave a certain region. And that's called a trapped region, and the boundary is called a trapped surface. Now, when do you call a space-time singular? There are also various possibilities, but generally the following is used. So space-time is called singular if it is time-like or null geodetically incomplete, and if the space-time cannot be embedded in an extended space-time. So if you are, say, as an observer on a time-like geodesic, this means that after a finite proper time you come to an end. You cannot extend this to infinity. You can extend this to accelerated curves and the like, but I think still the central version is for the time-like geodesic. So let us write this down. So definition of space-time is called singular if it is time-like or null geodesically incomplete, and if the space-time and if it, I think that the geodesic and if the space-time and if the space-time cannot be embedded in an extended space-time. Like we could for the Schwarzschild metric, I mean, to go from Schwarzschild to Kruskal, there was the Schwarzschild singularity, which turned out to be coordinate singularity, and so we could extend this up to the singularity at r equals 0. So if this is not possible, then the space-time is called singular. So if this with this definition and these assumptions, or this type of assumptions, then we have a singularity without assuming any symmetry. So this shows, I mean, very drastically that singularities is something we have to live with when we do general relativity. And okay, we don't think that there are singularities in nature, so they should at some point be avoided. We think that quantum theory in the form of quantum gravity avoids them. But so far we are within classical general relativity, and there are singularities. So Einstein's theory predicts its own breakdown, if you like, in this form. So it says that it cannot be universally valid because under very innocent assumptions space-time has an end. Now, after so much theory, we of course are also interested whether black holes can be observed, whether astronomers can make investigations and observations of these objects, and yes, this is true. So we will spend the next and last section in this chapter on astrophysical black holes. So thank you for today, and until next time.